So good morning, good afternoon, everybody. So thank you all for joining us today for a webinar on total energy model for connected devices. We will start in about 1 minute to allow other participants to join us, and thank you for your patience. So good morning, good afternoon. Thank you again for joining us today for our webinar on total energy model for connected devices. I'm Eme Bertoli from the Energy Efficiency Division of the International Energy Agency, and I will be moderating the webinar today. So I'm joined by Olivier Parada, Etienne Rebier, and Paola Cajamarca for supporting us behind the scenes. And I hope that you, your families and your friends are all well and remain so. So this webinar is organized with the Electronic Devices and Networks Annex, also known as ETNA, of the 4E Technology Collaboration Program. And this is part of our series on modernizing energy efficiency through digitalization. And for this, we actually thank Natural Resources Canada for their support for this webinar as part of their contribution to the IEA's work on this topic and to the Clean Energy Transitions Program. And we can equally thank the Super Efficient Equipment and Appliance Deployment Initiative for their support. So now to the substance of this webinar. So today we will present some insights on the energy and climate impacts of digital technologies based on IEA analysis, and this will be presented by my colleague George Camilla, Digital and Energy Analyst at the International Energy Agency. And we will then move on to zooming into a quantitative global model on the total energy use of connected devices that was developed by ETNA. And here we had a chance to see how to manipulate the various assumptions and view the changes in global energy consumption in real time. And this is something that you will be able to do on the webpage as well. And this section will be presented by ETNA's consultants, Paul Ryan, who is Director at Energy Consult, and Anson Wu, who is Director at Hansheng, and who developed the model. So we also have connected today Steve Belletti, who is the operating agent of ETNA, and also Terence Smith, who is Director at Mississippi Consulting and also worked on the model. So these presentations will be followed by a question and answer session. Please use the question and answer box that you have at the bottom of your control panel for questions so that we can select and read them out at the end of the presentations. We will not mention the names of people asking questions, and also please use this opportunity to suggest further topics or aspects that you would like to see in our upcoming webinars. Let me also remind you that this webinar is recorded, and the recording and the presentations will be available online. We'll send you an email and the link in the coming days. So now, without further ado, we can move on to our first presentation, and George, the floor is yours.
Thanks so much, Emmy. Really happy to be here. I'll try to provide a quick introduction into the broader energy and climate impacts of digital technologies based on some of the analysis we've done. So two contextual points before we get into that. First is that the energy sector is responsible for the largest share of greenhouse gas emissions globally. And within the energy sector, emissions are coming from many different sectors and services that use fossil fuels. So think about industries, buildings, transportation, power, fossil fuel production. So digital is a small part of that. So they have both direct and indirect effects on emissions. So in terms of direct emissions, these are emissions and energy use from data centers, data networks, connected devices, smartphones. But how they're used also affect emissions from other sectors. So think about how GPS and smartphone have enabled new transport services like Uber. And in turn, these also have secondary effects on other sectors. Think about how cities are designed, depending on how vehicles and transportation modes are evolving. So let's look first at the direct energy footprint. So the one thing about digital technologies is that they're growing very quickly compared to other economic and energy indicators. So if we look at population, GDP, electricity use, those have grown modestly over the past 2 decades. But if we look at the number of internet users, that has grown by 10 times, and internet traffic has grown by more than 2,000 times. So, many think that because of this rapid growth, there is a perception that energy and emissions have also grown increasingly rapidly. So there's a headline from Forbes in 1999 that predicted that the internet would consume half the US electricity supply by 2010. But in reality, that has not happened. Energy use from digital technologies has actually been relatively flat, especially over the last decade. This is while internet traffic has grown by more than 12 times since 2010, and demand for data center services has grown by more than 7.5 times. So there was an important paper published last year in Science showing data center energy use has been flat since 2010, consuming about 200 terawatt hours of electricity, which is about 1% of global electricity use. Data transmission networks use about 250 terawatt hours, which is just over 1%. So there are really 2 main drivers here that explain how data demand and energy use trends have diverged. So the first is that energy efficiency of computing and data transmission has been doubling every 2 to 3 years. So on the left side, you see the trend with computing, Kumi's law, and on the right, data transmission efficiency over the past decades. And for data centers, there's also been a massive shift from smaller, less efficient corporate data centers to more efficient cloud and hyperscale data centers. So together, those are contributing to the ability for energy efficiency trends to keep pace with this rapid growth in demand. And of course, tech companies are also leading the way on renewable energy procurement. So a few companies now are matching 100% of their energy use with the equivalent of renewable energy purchases each year. So far, I've just talked about the use phase of digital technologies, but of course, there are impacts throughout the life cycle of products, from materials extraction, manufacturing, transportation to the end consumer, and then of course, end of life and e-waste issues as well. And then in terms of the share of use phase versus other phases, typically as the device gets smaller, the use phase becomes a smaller part of the overall environmental footprint. So you can see in the right figure there that because of the incredible efficiency of some of these smaller battery powered devices, the manufacturing footprint is quite large. So there is a need to tackle those emissions as well from production. So what's the near-term outlook? Here's a headline from The Guardian a couple of years ago saying, the internet could consume 1/5 of global electricity by 2025. Many of these headlines you might have seen have actually come from a 2015 study taking this worst case scenario as this kind of what could happen. But in fact, he has actually updated his papers since. His revised results are much lower, actually. He's published as recently as 2010. But this just shows how difficult it is to predict kind of longer term trends, especially with this rapidly changing sector, both in terms of the way we use these technologies, the demand, and of course, the energy efficiency. And in terms of one specific use case, there's been headlines about how much carbon emissions come from streaming video. Here was one saying that half an hour emits 1.6 kilograms of CO2, equivalent to driving 4 miles. And our analysis shows that these numbers are 40 to 80 times too high. Of course, the overall numbers will depend on how your electricity is generated, whether you're watching on a big screen TV or a smartphone, because and in general, most of the energy use comes from the viewing device, especially televisions. And of course, we need to think about the counterfactual. For example, if, what are we comparing this to other activities? What is the, is it compared to renting a DVD or going to the movie theater? And of course, there's, secondary rebound effects we need to think about as the consumption of these services become easier and cheaper. What does that mean for overall demand? So there are effects, much bigger effects from digital technologies on other sectors. So we need to think about how to reduce both the carbon footprint of digital technologies themselves, but how do these affect other sectors? So a good example, kind of looking at the most direct effect, is teleworking, where we see, broadly speaking, the energy footprint of digital technologies is the same, whether you're at home or the office. The biggest increase in energy will come from your home energy use. So for cooling, heating, those things, but then that's offset by obviously the savings that you accrue from not commuting to work. And that depend on the type of vehicle you use, or if you're taking the metro or biking, the savings are obviously much smaller. And then critically, there are kind of longer term trends that we need to think about. So if we are able to telework almost all the time, would that change where people decide to live? Would people move outside of cities into larger homes, adopting different behaviors and then transportation patterns? That would have quite large effects on emissions compared to the, if we focus strictly on the digital side of things. So a couple of years ago, we published a report, Digitalisation and Energy, looking at how digital technologies could be applied in the energy system. So, these are things like in buildings, smart appliances, smart building controls and thermostats to optimize energy use. In transportation, things like shared mobility services, and in the future, potentially automated and highly automated vehicles, which, the energy and emissions trajectory of those technologies is highly uncertain because, if they're shared and automated and electric, then, there's a potential savings in emissions. But if they're, used like the vehicles today, they could actually lead to much larger energy use and emissions. And of course, many of these in general can save energy and emissions, but we do need to be worried about how digital technologies could be applied to increase energy and use and emissions. So if you think about IoT sensors and machine learning applied to the coal sector, potentially increasing the lifetime of coal-fired power plants, there's a risk that it could lock in further emissions from those technologies. Similarly, using machine learning to extract oil and gas at cheaper costs. So just a few key takeaways here before I turn it over to the colleagues to talk about the TEM model. In general, the direct energy and carbon footprint of digital technologies has been fairly flat over the past decade. And I think in general, the potential effect that they could have on other sectors for energy and emissions are very large. And we need to think about, how do we reduce the energy use and footprint of digital technologies? So through energy efficiency, renewables, innovation into more efficient technologies, but also, how do we design the right climate and energy policies to encourage the use of these technologies to help reduce emissions in other sectors and not make those worse? So with that, I'll close.
Yeah, so thank you, George, for this insightful presentation. So we're now ready to move on to the core, let's say, of this webinar with Paul's presentation. And while we shift screens, Perhaps let me just remind you that if you have questions, please feel free to post them in the Q&A box at the bottom of your control panel, and also feel free to post your comments in the chat. Thank you.
Thank you, Emmy, and thank you to the George and the IEA team for arranging this webinar. Can you see my screen now? Is it popped up?
Yes, thank you, Paul.
Good. So this is the total energy model of connected devices, and I just wanted to, before I jump into the slides, which are the intro, I will just also share where you can find this online now. So I'll just grab that and throw it up on screen. So the TEM is published on the IEA4E website /org Edna. So if you can see this link in the screen at the moment, you can also go there while we're doing the presentation. So it's iea-4e.org/Edna/TEM. And now bring back the presentation. There we go. So what I'm going to cover, and this is separated into 3 sections. So first, an introduction to the IEA 4E, TCP and Edna. Then an overview of the total energy model. Then a demonstration of the total energy model charts. And hopefully this will take about 30 minutes, and then we can go to questions and answers. And I might actually turn my video off for the moment, because it's causing my screen at the moment to go black and white. So just bear with me while I stop my video. On a rather skinny connection out in country area of Australia. So that's hopefully going to be a bit better. And I've lost the button to go forward. Thank goodness. First, the introduction to the IEA, TCP and Edna. Edna is the Electronic Devices and Networks Annex. Edna is an annex of the IEA 4E TCP, which is the IEA's technology collaboration program on energy efficient end use equipment. 4E and Edna are not part of the IEA. They form part of the collaboration with the IEA. Edna is focused on providing technical and policy guidance for energy efficiency for connected devices, and also the systems in which they operate. Their members are starting from Austria, Australia, and ending in the USA, but you can see them there all on the screen. The operating agent is Steve Beletich, and he's also here on the call for questions later on. So Edna's work focuses on the energy implications of connected devices to the internet. This can result in energy savings, but there are also an energy cost. For example, network standby, which is the energy used to keep a device connected to the communications network, even when it's not providing its primary function. Devices also result in energy consumption upstream in the data networks and the data centers. And Edna's total energy model seeks to quantify the total energy cost of connecting devices to the internet. Now, I'll go to an overview of the model. But first off, the TEM was commissioned by Edna and authored by Energy Consult. Its results do not reflect the views of the IEA, 4E, Edna, or their members. The TEM is a desktop model based on a wide range of assumptions and therefore contains some uncertainty. And the Energy Consult team includes myself, Paul Ryan, Anson Wu, and Terence Smith. Anson and I will be delivering this, this webinar, and Terence will be around at the end to help answer some of the questions. Now, context. In June 2019, Edna published the original total energy model referred to as TEM1 and the associated report. I gave you the link on the screen before where you can find that. The purpose in developing the TEM was to provide a quantitative model of the total energy use of connected devices globally. The TEM1 was developed as a flexible tool which could be updated as additional data became available and expanded to encompass new network technologies and devices associated with the rapidly evolving range of services over the internet. The overall purpose of the model was to provide a reputable source of energy use information on connected devices for use by energy efficiency policymakers in all jurisdictions and researchers. Broadly, the TEM1 modeled the energy use in two areas. The downstream, so that's the network connection component of the devices connected to the edge network and the LAN equipment made up of wired and wireless local area networks, and the energy use of the wide area network, the core, and the energy use of data centers. So that's in the upstream. Across these categories, the energy use was segmented into residential, business, and public sector, edge devices and network equipment types, and further segmentations, which I'll explain later on, for certain device categories. So we can separate the energy use into network standby and network active. It was intended for the TEM1 to model the energy use of network connected devices by region. However, there was insufficient data available when this was undertaken, and TEM1 was a global model. A further limitation of the TEM1 was that it did not categorize the type of data being transmitted and received over the network. So data related to the energy to general web use or media streaming was not separately identified. And so to overcome these limitations, 4E Edna has commissioned an expanded version of the TEM1, and it's called TEM2. So the scope of this modeling exercise, the diagram here illustrates the areas of interest and the modeling scope. So to the left is the upstream energy, which is made up of, appropriately in a cloud, the IP core network, the WAN or the access network, and the data centers. And these communicate to the connected edge devices. And we've separated the edge devices into three broad categories. Electronic edge devices, where we account for all of their energy use because they certainly just can't function at all without a network connection performing their main function. We have other edge devices where only the network connected energy use is accounted for in our modeling. So for instance, a connected light bulb, we account for the energy use of the network connection to the light bulb or the light itself, but not the energy used by the light in providing light. Similar for a connected fridge, we're accounting for the network connection, but not for the fridge energy use. Then we also have, and this is what was added for the TEM2, streaming media edge devices, when all of the energy use is being accounted for and attributed to the connected device when it's streaming media. So that's casting sticks and set-top boxes and obviously connected TVs. So we're including the energy use of the display in the calculations. Now I'll go into the model in a little more detail. So we've divided the model into an upstream energy model and a downstream energy model, and that's the total of the total energy model. So on the downstream side, for the edge device and edge network equipment, it's a bottom-up product stock model of energy use using the engineering method, meaning that energy use is estimated at the device level and summed to provide global and regional energy consumption. The methodology requires many data relating to the sales, life, and stock of the equipment, and combining with that with the energy use characteristics of the equipment, which all vary over time. In the upstream, For the DC WAN component, including the access networks, the approach uses specific energy intensity of the DC WAN equipment types per data traffic carried over the WAN. So the upstream energy use is calculated according to the share of data attributed to the various DC WAN technology types of the total projected traffic. The energy intensity, the energy use of per data transferred, or network efficiency, the share of the attributed to each technology, and the total network traffic also all vary over time. So the model is quite large and has over 1.7 million calculations going on. And the TEM uses over 200 different sources of information and thousands of product power measurements from the EDNA member countries, as well as many public data, such as Energy Star reported power data products over time, the US Consumer Technology Association's research, other 4E EDNA reports and research, and many of the member countries' registries and testing programs, data that has related to MEPS and labeling, and that captures the power consumption information which we have utilized in the model. So the devices are categorized broadly into 5 different categories. So for the downstream side, we've categorized the LAN equipment, the ICT equipment, entertainment equipment, automation, which is the broadest and widest of all categories, and security. And we've produced this so we could create a more aggregated view for displaying the information. Within each of these broad categories, we have subcategories. So for the LAN, for instance, we have access devices. So we have these subcategories within each group. So for ICT, we have PC, we have mobile, tablet, entertainment, we have display, audio devices, media devices, automation, which is the largest. We have automation equipment, automation connections associated with the appliances, associated with cooking, automation devices themselves within the IoT grouping, within lighting, space conditioning, and within security, we've grouped IP cameras. So that's the broad number. So there's, I think, over 77 different types of equipment which we've had to aggregate back up. So there's quite a large number of devices captured in the model. So the energy consumption categories are again separated into downstream and upstream. In the downstream side, to help us understand how energy is being utilized, we've created, we're using the various categories which are used internationally in the energy sector for some of these conditions. So the network active condition, which includes any state in which the device performs some function that requires an interaction with the network. So things like LAN equipment is often in network active mode, as we've defined it. Network standby condition, which is a low power mode with network connectivity and refers to the states in which the device is not delivering its primary or secondary functions, but retains the capability to resume applications via a network connection. And then this new category called media streaming condition, which includes the energy use of the edge device, so the connected TV or the PC or a separate display, when it is displaying and delivering streaming media. And so this is a new condition associated with the TEM2. Then in the upstream, we have separated the data and associated energy use into media streaming, including all of the video and audio that's delivered over the network, and non-media, which is everything else. Then there's additional categorization, and I won't go into it in detail, but we have 8 regions, which are based on the shipment forecasts, because we've sourced a lot of the shipment data from a research company called Juniper Research, who we paid for to obtain the shipment forecasts. We also have 7 IP traffic types, which are defined by Cisco in their VNI report. We've used those allocations to allocate our data usage to various device categories. So before we jump into the TEM charts on the website, I'll just give you a brief overview of the end result of the total energy model for all of the connected devices. So for the downstream, we have the network standby in the dark blue, and it's projected to keep on increasing to around the 200 terawatt hours by 2030. We have a similar amount for network active. And then for the device energy when streaming media, it's all added together to give us the downstream. Then in the upstream, we have the upstream energy attributed to streaming media and the upstream energy attributed to non-streaming. Now, I'll just focus in a little bit on the upstream because there is a lot going on underneath this. And here is a detailed graph from the TEM reports, which shows the underlying cross-section of energy consumption in the upstream. This is not available on the charts on the website, the TEM charts, but it's actually in the reports. So you can see here, building up from the bottom, we have the data center component, then the core of the network, and then the WAN in the other areas. So the blue is representing the data center component. This yellowy orange color is the core, and then the WAN, the wider area network, is represented by 2 colors. We have for instance, here in the dark green, the 2G radio networks. So the green is the radio networks, and the gray is the fixed area network. With the 3 or so different types of radio networks, we have characterized the energy consumption and projected forward. So we have 2G, 3G, 4G, and 5G. Here. And all of this has gone into creating that underlying cross-section of the energy consumption in the upstream. So now I'd like to demonstrate the TEM charts, and I'm going to be throwing up another screen here of the TEM charts. I'll explain what the chart items are and their features, and then go through some of the examples of what could be examined in each of the chart tabs. And there's 4 chart tabs. There's the base case and then 3 scenarios. So just bear with me while I bring up the total energy model. So this is the total energy model on the web, which is available at this site. And I'm just going to refresh it, and then I'm going to go back to it. So it's you can obtain the reports here as well, the detailed reports underlying this study. And I'm just going to go down a little bit, but my screen has gone black while I hope it's gone completely black, so I can't see what you might be seeing. It should come up again. Yes, I think we'll just bring up the underlying charts. Okay. So the underlying charts were built using a platform called Tableau, which is available in publicly. It can be used on any sites. And so we've uploaded a lot of the output data for these charts to be constructed, and it's quite an efficient mechanism. I'm just going to check with Anson or Amy whether the screen is still visible.
Yes, we can see your screen. Thank you, Paul.
Excellent. Because there's sometimes the internet doesn't actually work completely. So what I've done here though is I'm using the Tableau desktop application because it's going to be much quicker, and it means that I'm not actually seeking screen updates from the cloud at the same time as trying to share my screen across the internet. So as I mentioned, we've got 4 different tabs inside the charts. And the first one, and I'm just checking the time here, so I might go through these relatively quickly. We have the base case, which includes all of the information which I've described. Then we've got 3 scenarios which focus in on particular segments. So in this case, we've got the edge device network standby component, the local area network component, and the upstream energy intensity component. So we can adjust various input assumptions and factors to run scenarios in those ones. I'll give you a demonstration of quickly how you can focus in on a particular category. I had a number of them lined up, but I'll save all of them for later. The first one is, let's look at just the the automation category. So I'm going to unclick those that I'm not looking at, and you can see that the device subcategories that are still remaining are appliances, audio, cooking, etc. And now I'm going to focus in on the lighting component, and you'll see rapidly how also it changes, and then go back to the chart. So we're now looking at just lighting, and it's showing that the upstream, the majority of the energy, and if I just click on it, is being attributed to network standby. And that makes sense. The majority of the time, lighting devices, smart lights, are just left connected to the network awaiting an instruction. So they're in network standby mode. The chart also shows down the bottom the stock. So we're growing the stock to 2030 to about 3.2 billion. The charts can also show what would happen if you just want to look at Asia Pacific, for instance. And you can see the total number of devices there, or Far Eastern China, which should be substantially higher, or even North America. So these allow you to investigate by region the particular energy consumption and the stock calculated by the TEM. If I go to the IoT component, which is another very interesting one, where we'll see quite a different characteristic. There is a fair amount in network standby. The stock is leveling, the amount of energy in network standby is going down in proportion to the number of stock, and that's because of assumptions around their connection using low power radio networks. But they still have a significant amount of network active, and that's also due to the various mixture of devices within the IoT. There was something in the order of 12 or 15 devices that were modeled within that subcategory. If I compare this to something like audio, which is the smart speakers, not the display, not the smart displays, but just smart speakers, you can see that the stock is leveling off, and that is being projected to level off primarily because of the integration of that function will probably be occurring in more of the devices that we actually see around the home, such as connected TVs, which is occurring now, and possibly even LAN access devices. The voice activation is occurring on a large number of devices. However, network standby, even just for these, is quite large at 12 terawatt hours, and a very small amount of media streaming associated with it in the upstream. Oh, no, sorry, in the downstream. The upstream is virtually very small, virtually nothing there. Now, if I go to the next one, I could do the entertainment category. We can, or perhaps I'll just go straight to ICT. That's got quite different characteristics. And my screen has gone black again. Let me see. Yes, excellent. In the ICT category, we have mobile smartphones, PCs, storage, and tablets. About 6 billion total devices. Again, the majority of the energy consumption in this is in the upstream compared to the downstream. And that's primarily, if we look at just mobile devices, we should see a major change in the, yep, I'm getting it. Nothing works perfectly when you're actually delivering a webinar. I may have even lost. Can you hear me?
Yes, now...
oh, good. Good. My screen just went off. Thank you.
Now we can see the screen again.
It's having trouble getting out through the 10 kilometers of I'm on a wireless, fixed wireless network to make it to the ISP. So yes, with this particular category, you can see the majority of the energy use is in the upstream, in non-media and media streaming, and the very small, well, 6% of it's in the device actual consumption itself. So that's another example. Now I'm going to take you to the tab of, just getting back to my notes. So I have to, the screen is going wild here. Going to edge device network standby. Now, within each of these next 3 tabs, we've implemented an ability to adjust the underlying forecast energy consumption of the products as they're entering the stock. So, for instance, in this case, 100% represents the BAU. But if we wanted to, say, reduce the edge device network standby by 75%, we would select 25%. So it's going to be 25% of the BAU consumption. And this tracks through the stock and shows the change, the potential change, if there was policies or programs or technology change, which improves the efficiency of the devices within in network standby mode. And you can see that it starts to level off because by this stage, most of the earlier devices have been retired, and we're now just at the point where all of the new devices are starting to, with that 25% of the energy consumption of the BAU, are becoming dominant in the stock. You can also go the other way. So I'll go back to BAU, and if there was an increase, say, of 50%, we would select 150. And you can see the dramatic impact that makes also. So this is just changing the assumptions around the consumption characteristics, the power consumption characteristics of the products in network standby. Now, local area networks, we've also isolated out here each of the product devices within that category. And so we can see the impact of the particular devices, such as integrated access devices, which is what is probably everyone is connecting through at the moment if they're connecting from home. Again, we can change the assumptions. So for instance, if I just wanted to focus on integrated access devices, I would switch off all of the other devices on the graph. And we'll say we can reduce that by 50%. We get a radical change in the projected consumption going forward. But similarly, if we went back to the BAU and then said, well, it's actually going to be 50% higher, the consumption increases. Now, Anson, I would like you to take the audience through the upstream data intensity, the data centers in the WAN. Are you there, Anson?
Yep. Can you hear me? Hello, everyone.
Yep, I can hear you. So
okay, fantastic.
You can go for it. You can tell me what to plug and play with.
Okay, so the upstream energy is, as Paul explained earlier, is split between the energy used for streaming media and the non-media, and this includes again the data centers and the networks, the wide area networks. And you can see that the upstream is, in terms of energy, is much smaller, despite the fact it consumes over approximately 80% of all the data being consumed. And this is simply due to the fact that streaming media is a very simple process. It just comes from some sort of hard drive or efficient storage device, and then just spits it out straight to your device. And then they can put the servers as close as they can to you. Whereas other types of websites or processing and things like AI can be very, very processor intensive. And so we see that this, some of these reports and headlines are perhaps a bit dramatic. The other thing is to see that, again, George showed that the number of users is increasing, the amount of data each user is increasing a lot. And there is very high increase in data consumption. And the reason why energy doesn't follow this is that we have increasing efficiency over time, better technology across all the types of things like the data centers, moving from 4G to 5G, moving to fiber broadband and things like this. And this has given us, in the business as usual, when we take everything into account that's happening, approximately a 19% improvement in efficiency per annum, and leads to a relatively flat energy consumption over time. And so what we can do with this model is also change the scenario. So we look at a 0%. So in this scenario, we're saying efficiency is frozen, technology somehow is frozen in time. And this would be how our energy just skyrockets as data consumption increases. This isn't a realistic scenario. I think you need to understand what would happen economically. What would your Netflix subscription price be like if this is what was happening? So we see something, and this is like some of the earlier models. And then we return to the 19%. I think one of the questions is what happens if technology starts to slow down? So if we select, say, -12, so we can see scenarios, if we don't achieve future increases of technology, then energy consumption could increase. We see it doubling because it's very sensitive. Because the data is increasing so fast, it's very sensitive to this efficiency improvement to offset this. So we could have a -12, but similarly, if we manage to increase the efficiency, increase the technology, or in fact deploy the existing technology better, which is often the case. So we say like a 3% improvement over 19% to -22. Thank you, Paul. We can see we can actually have a very drastic and quite fast reduction in energy, perhaps a reduction of 25% with what looks like quite a modest improvement in efficiency. There are, I think that's about it. And again, we have the regions. One of the things we can't do with the regions is we cannot say this region uses this type of internet. So it's very much based on sort of a global.
Yes. Yeah. It was. We could not get into it. The detail and the information available was not there.
Yeah. So the region is sort of attributed by the number of devices in that region rather than a detailed analysis of the networks in each region. So that, when we look at the energy forecasts.
Yeah. So Anson, I think we've reached the end of this, and we've only got about 10 minutes left for questions. Is that correct, Amy?
Yeah, thank you very much, Dan. And we actually have a couple of questions.
Stop sharing my screen somehow. I've lost the controls. Can you actually take over the screen? I've actually lost control. Like, yeah. I think I've got it back. Yes.
Perfect.
Right.
So in the interest of time, we'll just move to a couple of quick questions that we received in the Q&A. And thank you for the participants who already posted some comments and answers. So I see a couple of questions and comments related actually to industry. So there was one more along the lines of what do you think, like since TEM is considering consumer energy consumption of connected devices, how this might change, or you think it might change as we move into more connected devices, also manufacturing and distribution facilities. But also we had another question related to digitalization of industry and cloud computing. Since it's one of our participants actually had a look at the report and was wondering whether the digitalization of industry and cloud computing can be negligible compared to the entertainment data, or what is your view around that? And I might ask you maybe to keep it quite short, so we might take on other questions. So I don't know whether Paul or Anson.
Oh, sorry, what was the question?
So we had two questions actually related on consumer and energy consumption of connected devices related to industry and manufacturing, and increased digitalization of industry and cloud computing versus entertainment data, for instance. Like what is your view about what might happen, let's say, if we move forward towards an increased digitalization in other sectors and connected devices in other sectors as manufacturing and others, for instance?
So I'm not sure I understand the question, but anyway, look, it looks like consumer end use equipment is generally being connected by Wi-Fi at the moment. A lot of it is. And if it continues, that's going to continue a higher level of network connected standby, because until we move to Wi-Fi 6 and everything is all of the infrastructure is upgraded, including the access devices, then network standby is still going to be a large component. Whereas as you move into the manufacturing and distribution centers, Anson, you might want to consider that one, considering our recent work. A lot of that is not as, the connected device energy is not as high.
Yeah, so as Paul mentioned, clearly everyone expects this to increase in terms of number of devices very rapidly, and there will be some energy associated with this, but at the same time, the sensors are relatively efficient, especially when you look at how much the industry is using as a whole. And again, it comes to this idea of how much sort of possible savings could come from this, and how do we guide that. But also in terms of the amount of data being produced, it's not huge, and also it's probably not shooting all the way across the internet, across to the cloud, simply because if you want real-time control, you need it to happen on site probably. There's also data security issues you want to consider and things like that. So, you know, there's a lot of uncertainty, but at the moment, and especially in the shorter term, it's unlikely to be as massive as say something like media streaming, simply due to just the sheer volume of data that a video creates.
Okay, thank you very much. Then we received another question related to 4G and 5G systems, and the question is around the lines of if you had a look at these systems, at the power models for 4G and 5G systems, and perhaps you might also give us a bit of an overview on how you see 5G impacting the energy use moving forward.
So we looked at 5G, but there's obviously a limit to the amount of information and the amount of depth we can go into looking at these things, especially when deployment is so early. Terence or Terry, if he's on the line, might want to chip in here. But looking at from in terms of like the amount of energy used to transmit data, it is clearly much more efficient. We're relatively quite conservative about how efficient it is, in fact. So we don't say it's as efficient as it, you know, absolutely could be. And I mean, I'm interested to understand sort of how this is playing out in the real world, and whether we want to revisit the assumptions and relook at the model. But at the same time, I don't get the sense that, you know, technology is freezing. There's some sort of problem that cannot be overcome, and that efficiency won't be able to improve over time.
Okay, thank you. I don't know whether Terence would like to add some comments on this, and if not, I actually have another question pending.
I could quickly just sort of add a comment, Emmy, in that currently, you know, 5G has started to roll out, but the thing that sort of hasn't been rolled out yet is that component of 5G, which is referred to as the millimeter wave component. And the question, you know, refers to the sort of higher density networks that happens once you start using that sort of millimeter wave. And in terms of the sort of energy use, I mean, there's a lot of consideration being given to this at the moment. When the original planning for 5G was done, and the ITUT sort of published its goals about IMT 2020, they were talking about sort of 5G, the energy efficiency should be no worse than what 4G would be. And when you consider then the amount of increase in sort of, you know, data rate, we're talking about sort of 10 times the speed, and sort of even higher for sort of peak rates and low latency and all that sort of thing. In that sense, what happens is that 5G, under certain circumstances, could be seen to be sort of even more efficient, because depending on how much extra power that it might take to sort of run the network, we really don't know that just at the moment. So I guess it's, in answering the question, I'd have to just say we have to wait and see.
Right, thank you very much. So maybe we'll just add in a very quick question, and hopefully the participant can bear with us for a couple more minutes. So we received a question around what priority areas should policymakers focus on. I don't know if you have some, you know, quick priorities, quick recommendations, or areas where they should be focusing on first.
I'll give one really quick go. The priority areas, policymakers can focus on is where they actually can have an influence, and it may be in helping to guide and understand the standards for the various radio devices that we're using for connecting to the internet. Primarily, if you use low power radio devices, then we cut the network standby down by to 1/100th of the energy consumption. It's a massive change. Wi-Fi 6 has got some elements of that in it now, but all of the other more appropriate networks for such small data transfer, such as NB-IoT and LoRaN, they all have greater capacity. So if you use the network that's appropriate for the use, it would be maybe some guidance on that. But certainly we can't do a lot about streaming. It's happening. Anson, you might have some views on this, but I can't see us changing the characteristics of streaming. That was, I think, in there as well.
I'll just add, in terms of policy, what we see is a lot of legacy devices, and this can hold back the efficiency. So when we look at the 2G networks still operating, the 3G networks that are still operating, if we go back to that slide, I don't know if anyone can recall, these were consuming as much energy as 5G, whilst doing virtually nothing by 2030. The ability to remove those is very important. At the same time, the policy is easy to look back at the policy and say, this is happening, this has happened, we need to do something. And this is the case with something like streaming. And then going forwards, it looks like you need to say, as George has mentioned as well, we need to see how we can guide what's happening in future to the best effect. How do we implement them? How do we make them efficient? Rather than comparing it to DVD or something and saying, oh, DVD may or may not be more efficient, but it's happened and we would never have been able to stop video streaming. So, we just got to make it as efficient as we can.
All right, thank you very much. So yeah, a really nice way to actually end with some concrete recommendations for our policymakers. Given that we're running slightly over time, thank you for bearing with us. And first of all, I would like to thank you, our honorable speakers, but also our participants, for being with us today. And we really hope that this tool might be useful for the work that our audience is carrying out as well. So please stay tuned on our social media channels, including the LinkedIn group IEA Modernizing Energy Efficiency through Digitalisation. As I mentioned earlier, we're going to share the link with the registration and the presentation, so you can access it even in the future. Stay tuned also on our website calendar for our coming up meetings, and stay safe. Thank you.
Thank you.
Thank you, Amy.